we talked about analytics in the morning. We talked about distributed structured stores in the first session in the afternoon. So the second session in the afternoon is really focused on how to store really large amounts of data on a somewhat tight budget. So we have 3 talks. The first talk is by Kestutis, who's going to share how Facebook really approached storing, like building a specialized solution for rarely accessed data that gets accumulated. Right. Kestutis?
Thank you. Good afternoon. My name is Kestutis Patiejunas, and I want to tell you a story how at Facebook we were building storage to store cold data. So we build these cold storage systems, and this presentation will be about the journey of building them. So first, when Facebook was founded in 2004, they had 0 users. And then in 2012, we got 1 billion users. Now, in 2015, we have over 1.4 billion users. Of course, what do? They post pictures. They post lots of pictures. And these pictures are very hot in the beginning, and then they get more warm, and then they get cold. But these pictures cost us money to store, and we cannot lose anything. We can always need to keep them. So Facebook realized that buying storage systems from companies like EMC, NetApp will be unsustainable. It will be way too expensive, and we will not be able to support our users. It was necessary to build our system, and it was necessary to do it by thinking from ground up, from data centers to the software. So in 2012, at Facebook, initiative was started to build such system. And we started to design from data centers, special servers, and special software. And I want to tell a story about how we built it and what was built. But before I go to this, let's look at 1990. And at that time, we had these hard drives. So I have one on the table. And this is what's under this sheet. I will be very careful to, and I think it's an amazing piece of machinery. What is even more amazing, that often it even works, and not this time. Oh, it's working. It takes time to spin up. And soon, heads will start moving. Did you see it moving? Yep. So I have a quick quiz. I want to ask you to raise hands. Who was born after 1990? Okay, looks like more senior audience. Who learned to read after 1990? Who was not reading at the time when this drive was made? Okay, at least somebody. Who was not coding? Okay, at least I hit something. Who didn't have a driver license? So what's amazing about this piece of equipment, besides the fact that it still was made in the United States, it's a size, the physical size, and all these parameters what we care about. Like, what's the capacity? 300 megabytes. My iPhone from last year, before Facebook upgraded it, had like 16 gigabytes. And another one, the last line, data transfer rate, 1 megabyte per second. And at that time, I remember paying something like $900 for this one. This was like amazing. This was so expensive. So my point is that over the time, in the last 25 years, these hard drives, we went from 300 megabyte capacity to 8 terabytes, and Seagate just announced 10 terabyte hard drives. It's close to exponential progression in capacity. But at the same time, when you look at the time, what it takes to retrieve data from these hard drives, you could read this whole hard drive in 5 minutes. And it takes 18 hours, close to 24 hours, to read all the data from the biggest hard drive in these days. So in 2006, Jim Gray noticed this and made like very famous statement saying, tape is dead, disk is tape. And to some degree, we were inspired by his statement, and we built cold storage system based on disks. We're using them almost like tapes. So now in 2012, when we decided to do end-to-end solution, optimizing data center servers and a software, we built the system. This is a picture of our data centers in Oregon. You see that little building with a blue roof? This is a cold storage data center. Because it's a cold storage, we do not use lots of electricity. We don't need to do lots of cooling. It's about 5 times cheaper per square foot than the other big one, which is for warm storage or for active computing. So we optimized building cost, and that translates at the end at the total savings. Going from the building construction costs and special data center design, we did special design for our storage racks. It's a special rack designed just for cold storage. It has 2 computers and lots of sleds with hard drives. In these sleds, hard drives are packed like sardines. What's important for us to know is that out of these 15 hard drives, only 1 will be powered at one time. That's why it's called cold storage. All others are cut off. They're not even powered. They're consuming no electricity. It means that we don't need to cool them. So we use about like 6% of hard drives which are available. So this is interesting to talk about hardware, but all of us are software guys, and we want to hear about software. And this is my story about software. So we started to build cold storage in 2013. And we set in the beginning with very distinct principles. We didn't want to build another general purpose storage system and get diluted with all these goals and not to be optimal. So in our principles, we said like, what's important, what's the goal, and what's not the goal. And I want to walk through them so you will understand why and how we build this system. We wanted to make it durable. It's no value of storing data if it's not durable, if I lose it. We wanted to make it high efficiency. We knew that exabytes of data will come. Availability was okay to be reasonable, meaning if it's like I'm storing as a secondary copy, as a protection from disaster, it's okay if it's not available like immediately. Scale is super important. I want to have very good scale so that I can buy new technology, new hard drives, and the new data can be stored. And evolution is very important. Technology will change. Lifetime of the buildings is like 30 years. I have to be ready for evolution, that the next year will be 10 terabyte hard drives. Last one, important one, was that as system gets bigger, it should get better, not worse. And I said, like, we should not care about latency, about high availability. We should not store and care about storing efficiently small objects or objects for very short time. And we also had these principles, that durability will come by eliminating single points of failure. And if something fails, I should be able to recover my data from pieces. And for efficiency, I will get by trading latency and having queues full of requests. So latency will be big, and I will be not like very quick to respond, but my efficiency will be big. My system always will be busy. Simplicity will lead me to reliability. I will make some system very simple, componentizable, and very important that we want to handle failures from day one. Because if we don't handle them, then we say like it will be in version 2 or so, eventually we will never implement them. We created good architecture diagram, and it was like kind of like simple model where data will come from the top, will get encoded by these front ends. We use Reed-Solomon encoding. will go over the network to these storage nodes where we have all these hard drives, which only 6% of them are powered up. As we implemented system, we achieved some good operational characteristics. At that time, and we still have a system at Facebook which uses a RAID from some hardware provider, hardware manufacturer. So I cannot tell which one. Lawyers asked me to black it out. So it used to be that if one hard drive fails, RAID takes 20 days to repair 4 terabyte hard drive. In our system design, we wanted to build a system where hard drive could be repaired in under 7 minutes. How it's possible? We're not repairing one hard drive into another hard drive. We're repairing an equivalence of information. If one hard drive failed and it had some information, the equivalence of this information is recreated in a distributed way into all our hard drives. We also got system to get better and it gets bigger. As nobody buys immediately 1 exabyte of hard drives, as we deliver these racks and install them, the data which we are storing in these systems is being spread across many of them. And as system gets bigger, we can write and we can read more and data and we can do it faster and faster. So in 2014, we went live in production. And since then, we haven't lost yet a single byte of data. It took 9 months for us to get into production. It's about the same what Mutu told about ZippyDB. It must be some gestation period for the software at Facebook. And I have a question. So 9 months to get it in production from 0 to production ready and operating system. How many engineers do you think we had? The answer is very simple. We had 4. And I have all the rest of the 3 guys in the audience. So can you stand up? Mohammed, Ritesh, and Vinchao. Thank you. So it wouldn't be possible without you guys. It was fun to work on this system. So how it works? We have a set of machines where when data comes, it gets transcoded by using Reed-Solomon, and we produce many of these shards. We use 20/28 encoding. And that data gets stored into these storage nodes. These storage nodes are these racks with computer with lots of hard drives packed as sardines. We also have a bunch of these services where we do garbage collection, anti-entropy, we scrub these disks, we check for errors, and we see that data is still alive and durable. And we have some other additional services. And when we need to know where are these hard drives located, we use simple SQL database because the number of the hard drives fits easily on the modern SQL database. So besides implementing storage system, maybe 6 months before Kim Jong-il hacked Sony, we said we need to be serious about this, and we also added security. We used secure thrift, that's Facebook's implementation of RPC with Kerberos to secure access between our services. And the same was important to do for audit. We want to be able to know who is retrieving, who is reading, writing this data. It cannot be just the black hole where anyone can access it. Raw disk storage. This is an important and interesting point. We started to implement the system by using XFS file system, but we knew we will need to change. And here is why. You have seen that slide with this old hard drive. It takes about 12 to 18 hours to fill up this hard drive. If I delete files in a use file system, I can delete all the files in 1 second. So it seems very disproportional. It takes so long to fill it up and so quick to delete. That was one of the reasons why we created raw disk file system, meaning we're not using file system at all. We're writing information sector by sector. And to delete such information from such hard drive, you literally need to overwrite every sector. So if Kim Jong-il sends his guys, they have to be in our network for a long, long time. 2 seconds will not do a damage. So is this is good enough? What happens, fire, storm, earthquake, and all these other bad things. What else, we need to do, like if we want to have our data stored in a reliable way? And we thought about doing Reed-Solomon encoding between data centers. It's a higher level concept where I would say, how about my data is spread not between racks with machines, but it's spread between data centers. And if I have few of them available, let's say I use 3 data centers, and if my 2 of them are still available, I can retrieve my data. This way, conceptually, I'm thinking I'm doing RAID between them, and I'm trading network and CPU for durability and availability. So when I was preparing for this presentation and I was thinking what message I want you to walk out of this event, I wanted you to think about this. In the 90s, when this hard drive was made, state of the art was to do RAID. People would put many of these hard drives in one machine, and not to lose data, they would be doing RAID between these disks. Then, like in 2000s, we got smarter and we did what we did. We did like RAID between many racks, RAID between machines. And now in 2015, we are doing RAID between data centers. So conceptually, we started with like small scale, RAID between hard drives, RAID between machines, RAID between data centers. Or you could substitute it with Reed-Solomon. So back in 2015 now. So Jim Gray said that 10 terabyte disks, and you look at the slide deck, should be by 2011. And Seagate just announced like recently 10 terabyte hard disks. So he was not like very precise, and we definitely not $80. What is happening is that hard drive industry is hitting the wall of density. We're not capable to produce hard drives of the higher capacity. We're adding platters. We're trying to pull one-off tricks like SMR, shingle magnetic recording. And everyone is waiting for HAMR, but probably it's not going to happen anytime soon. On the same time, optical has like 100 gigabits going to 300 and gigabit per disk, per Blu-ray disk, and probably will be 1 terabyte Blu-ray disks. It's also what is a pressure from industry and from business side. Less and less demand for hard drives like this. Probably most of you in your laptops in this room don't have a single hard drive and just SSD. So less and less incentive for hard drive vendors like Seagate, Western Digital, Toshiba to produce hard drives of a high capacity. Less money goes into that, less money is spent on research and development, and less output. At the same time, 4K movies, 8K movies, like 3D used to be popular. So there is a demand on another side. So at Facebook, we were thinking like we need to be able to pivot, and we need to be able to look at like what are our alternatives to store data. And we created BluRay storage rack. It's literally a big jukebox size of an industrial data center rack. Inside it has a robotic loader which goes, opens a cartridge, takes a Blu-ray disc and loads it in one of the burners. When you look how it's built, it's very simple. It's lots of mechanics, one robot actually, lots of cartridges, multiple burners, and a computer which controls that robot, controls burners, and puts that data into these Blu-ray discs. Of course, when this system will be operational, and it's quite soon, it has to be part of overall cold storage at Facebook. So this is a diagram of our plan. Data from the cold storage, which is built based on hard drives, will be sucked from these hard drives, from these like cold storage racks, transcoded into different encoding, and written into Blu-ray racks. So as we look at this timeline from 25 years ago, you probably will wonder what's in the future. You probably will think like, what's ahead of me? And It's too disappointing, but I cannot predict the future. I have no idea what's ahead. I only know that me being a software guy at Facebook, I need to think about these things. One thing what I wanted to communicate is this. It's like when data amounts are massive, efficiency is important. So if I'm building a system which is, few terabytes or so, I could not care much about savings. When I'm doing multi-petabyte or exabyte systems, I know that my savings will translate in very big financial savings. And I will get these savings and efficiency only by specialization. So there are two famous laws. One is Moore's law and another one is Kreider's law. Moore's law about transistors. Kreider, I think this dude was one of the founders of Seagate. It's a similar law, equivalent law for hard drives. So these laws are stalling. The processors are not getting faster and silicon is not getting much denser. And the same is happening with magnetic recording. So if these trends are not true anymore or they're slowing down, the question what I want you to leave out of this room would be, which of the technologies, magnetic, optic, flash, tape, will have few more iterations left where we'll be getting like 10, 20% year-over-year improvements. Thank you.
Is this separate, or do you have, the question I had is two-part question. One is, do you ever have cases where any data, be it a picture or a media, ever goes from being cold to being hot again? And how does either of your system, basically the optical versus the hard disk, kind of ever do, or is that a completely different system?
Yeah. So I can give such examples of what data goes into these systems. So imagine the hot data, the picture what you just posted, hopefully about me on the Facebook, cannot go to the system. A retrieval time will be like 2.5 hours, so it's unacceptable. And nobody knows, when my picture will become cold. But at Facebook, we have to have a protection for these pictures. So we want to be able to do like very good and quick engineering and innovation on our mainline systems, but to have a safety net. So we want to have every picture as soon as it was uploaded backed up in a cold storage. If our mainline systems have some problem, we should be able to restore.
So this is separate from your actual real-time, kind of like a lookup kind of?
Yes, we do not put real-time, we might put real-time data into the system, but we will not serve it as a real-time request.
Okay. Thank you.
So this is separate, the cold storage, and you mentioned some even power off and on the storage disks. And how would that be, what's actually going to be triggered power off, and how that will be triggered power on again and doing the management?
Good question. So like I said, we have in every tray we have 15 disks, and we only can have one powered at a time. So we had two choices. One choice was to power on when it's needed, and another choice would be to power on schedule. To power on when it's needed would be like big complexity. Imagine solving on these all the linear programming equations with like 500,000 disks. Would be very, very complex. I went for the simple solution. Each disk would be powered on for 10 minutes at a given time, and I can calculate that time any time in the future. So they all powered on at a schedule. That's why when you need to retrieve some data, it can take 2.5 hours to get your data.
How do you detect entropy errors and bit flips if the hard drive is powered on only for such a short time?
Only few people know what I'm smiling. Why I'm smiling? Oh yes, it's like so non-trivial. Brian Beach has a presentation after me and Aaron, and maybe he will go more in this one. I can tell you like few technical points. We do scrubbing. Scrubbing would mean like we read data and we compare the data with a checksum. We look at smart counters. We look at the errors, what happen at the application level when we're trying to read data and data is just not reading. And we also look at the speed of these reads. So if my hard drive should be reading about like 80 megabytes a second, 100 megabytes a second, if some hard drive is reading at much slower speed, I consider this hard drive to be bad. We still have ongoing big debate at Facebook how to decide when do we shoot hard drive in the head.
When the hard drive fails, are you repairing them or let them stay dead?
Intention is when hard drive fails, we have a big industrial shredder, and these hard drives are shredded.
Thanks for the great presentation. So I have a quick question about, so did Facebook ever dealt with a situation where you have to do a mass recovery of the data and you are limited by the ability to upload the data from a data center because all of the data, cold storage data, is actually stored in one physical location, so you're going to be stuck with that. Did you guys have any kind of logic to circumvent that situation?
So could you speak louder?
Sorry. So my question was that did you ever, Facebook faced a situation like, Gmail faced a situation a while back where they had to recover lots and lots of data and their ability to recover faster was limited because everything was stored in one place. So does Facebook have any kind of mechanism to overcome that kind of problems, and what kind of mechanism you guys have?
I'm still not sure that I got it, but if I will answer incorrectly, get back to me later. So if I understand your question, will we be able to retrieve that data when we need like lots of it? And if I'm powering on a hard drive, how much I will be getting? If that's a question, so imagine the data flows in the system are humongous. We measure it in like tens or even like hundreds of gigabytes per second. If somebody is putting petabytes of data into such system, as it goes in, it goes all across all the hard drives, all these racks. When we want to retrieve it, most likely we're retrieving not because we lost one file, because some big system which serves live data has to be restored. At that time, I need to retrieve multi-petabytes of data. So my hard drive scheduling and retrieving of the data, it's not that important. I can read from whatever hard drive is available at this time, and at the end I will suck in all the petabytes of data. But I'm not sure, I'm looking at your face, not sure if I understood your question.
I think I'll sync up with you later.
So, but let's please sync up after this.
So, I have a question. So what is your cost model? Like if you compare to Haystack, how more efficient is the disk system and the Blu-ray system? Do you have a cost metrics of how this plays out, especially with cooling and all taken out?
I don't have a data here. I think in OCP meeting, OCP event this year and previous year, we had like this presentation. So what I can tell is that like now we're approaching that point in time where storing data on disk versus storing on optical, it's about the same with the current technology. The big hope is that optical will have one or two iterations ahead in density, and that cost will go down. Also, optical has this advantage that these Blu-rays, they're not Blu-rays, they're like optical archival disks. They have a longer longevity, so the lifetime could be like 10 years. This hard drive, probably has operational lifetime of 3 years, so your data could stay for longer. But you have to have a data which makes sense to keep for 10 years. There is also another advantage where data on a Blu-ray, guess what, cannot be erased by these, North Korean hackers. So it's like much, much more reliable. If you really have a data which you want to protect, it's not bad to have it on non-erasable media.